All right, so we left off last time on our crystal lattice imperfections with the vacancy, basically a missing atom, and then the interstitial C, which would be a different atom of a different element occupying some vacancy defect in a crystalline structure of a main alloying element. So, moving on from that, we're going to start to get into um, metal alloys a little bit more. So we talked a little bit about metal alloys, but what I want you to take away from this for the preparation for the test is that metal alloys are created before a forging process takes place. So, i.e., the metal alloys that we're talking about are going to be created when the main alloying element is molten and before that is cast into an ingot. So it's added in while it's molten, and then the ingot is then forged after the fact. Now there is a process known as forge welding, and you can um, forge two different types of steel together, or two different, it doesn't even have to be steel, it could be different materials altogether. And you can forge those together, but those don't really create an alloy that creates a non-homogeneous mixture of two different materials. That's why, like the Damascus and all those things you see that are real popular now, have a pattern, and the pattern is representative of the two different materials. So you can see the materials haven't really mixed together. Um, it's more of a trail mix situation than actually making like bread or like a cake, if that makes sense. So we're also going to talk about the extrusion process as well as the forging process in this video, and then we'll talk a little bit more about some additional processes going forward. Now, what you're seeing in front of you is a picture of the direct extrusion process. So this is can be done at different temperatures depending on the alloy. Generally, like let's say for aluminum, the aluminum is heated to within a certain percentage of the melting point. It's not molten, it's just very, very hot. And then they would press it through a die and create an extrusion. There are also cold extrusion machines, like you can do lead and tin. Some alloys that have um, face-centered cubic body structures that aren't very that slip a lot easier than let's say a body-centered cubic would. So that would be your golds, your copper, all your alloys that you can hammer out really thin. You could also do a cold extrusion process. You can also do a drawing process, which is basically the opposite of an extrusion. So here we're pressing on the material and pressing the extrusion out, and with a drawing process would be the opposite of this. You would be pulling the material through a die, and it would be sizing it on the back end, and you would be pulling it through. So that happens with a lot of different types of materials. So we're also going to talk a little bit about the addition of grain refinements. So when the alloy is molten, and let's say it's not going to be a forged product, it's going to be a cast product, remember that the addition of grain refinements can help control, like we saw in the last few slides, can control the grain size and structure of certain pieces of the casting or the entire casting itself, depending on what it needs to accomplish as its life as a part. So keep that in mind going forward for the test, for test 2, and we'll continue on. And what we're going to get into now is the forging process. So we've touched a little bit on the elastic and plastic deformation, so we're going to kind of review that. Remember, elastic like a rubber band, if you pull on it or load it, it's going to return to its original position. And a plastic deformation would be like a tubing bender. Once you bend it past a certain point, it's going to stay bent. And that would be a permanent deformation, so it's not going to spring back. Keep in mind, If anybody's ever bent tubing or anything like that before, even after there is a plastic deformation, there still is some spring back, and that's due to part of the material not completely getting into the plastic deformation zone. And with tubing, the way it's shaped, you'll never get all of it, all of the cross section uniform, so there's always going to be some spring back, and that's why when you're bending tubing, you usually go over a couple of degrees so it springs back to the bend angle you want. So definitely have a good understanding of plastic and elastic deformation. Hot and cold forging. So we talked a little bit about extrusion on the last slide. So with forging, it's a similar process, but I know we watched a few videos on it. It's creating plastic deformation of a part. So you can do it with a hammer, you can do it with a giant roller, you can do it hot, you can do it cold. But at its simplest form, forging is just shaping a material by exceeding its plastic deformation requirements. So exceeding its yield strength to where you're into the actual plastic deformation. Not necessarily going past its ultimate strength, which would be breaking it, but going in between those 2 points on the graph to where you're actually creating permanent deformation in the part, as well as the cross section of the part. So one thing we need to know about hot and cold forging for the test is cold forging requires bigger machines, bigger machinery, more powerful machinery to create this same deformation. And the reason is, you can kind of think of it all as like energy accounting. We're throwing a lot of energy into that part or into that piece of steel or whatever it may be. We're putting a lot of energy in the form of heat into that part. And if we're cold forging that part, we're not going to be putting that energy into the part to start with. We're going to have to do all of that work with the machinery at room temperature or some temperature well below the recrystallization temperatures that you would want to reach before you did any hot forging. So keep that in mind. Cold forging is less efficient as far as the machinery. Hot forging, the machinery needs to be resistant to the heat, but it doesn't need to be as strong or as formidable as it would need to be for cold forging. Another point we need to cover for hot and cold forging is the cold forging process generally leads to more brittle parts, and that's because the grains aren't being moved around while it's above its recrystallization temperature. So what that means is the grains are really still kind of in that transition point to where they haven't really formed yet while it's being forged on. So when we take the heat away from the part and we cold forge it, it becomes more brittle because those slip deformations in the crystalline structure have all been compressed, and there's really nowhere for the material to deform anymore. Whereas if it's been hot forged, the grain structure and all the way down to the atomic structure, all of the slip deformation defects in the crystalline structure aren't filled up yet. They've all been formed that way because they were formed at a higher temperature, so they weren't actually slip deformed against each other. The grains were kind of able to move around a little bit more, whereas in a cold forging situation, you're just deforming the grain structure you have and compressing that grain structure and taking up the slip deformation defects and filling those up to the point where the part becomes brittle. But you can also, after you do that, you can what we call normalize the part or temper the part and kind of reset the crystal structure inside the part after the cold forge, and the part would normalize and you wouldn't have that brittle part. But that would be kind of undoing what we had done to start with. We do a lab in person, and we generally we test this. We do a hot forge piece, and we take a piece of steel, usually spring steel or some tool steel, get it really hot, beat on it, beat it into the shape of a wedge or like a little axe, and then we let it air cool, and then that's our hot forge test piece. And then we take one with no heat at all, and when we do this in person, it becomes very evident that you're putting more energy per blow, because when we do a cold forge, we have to use a hammer that's like twice the size to get anything done, and it still takes a long time. It's a lot of just beating on it and trying to beat it into shape. And eventually we do beat it into shape. And then we leave that one alone, and that one's our cold forge test piece. And then we do one more, and we forge it hot, so we heat it up and beat it into the shape we want. And then after we get the desired shape we want, we do one final heat, and we get it really hot, get it cherry red, glowing red, and then we quench it into water. And then what we do is we hammer those test parts together, and we kind of see which one wins. Since we weren't able to do that, I can just give you guys the spoiler. So the winner is always the heat treated piece. So when we do that quench, that hardens that part to where it is substantially harder than the other two, and it will cut into the other two parts. Now the place for second is usually a surprise for a lot of people. Second is always the cold forged part. So the last on the list is the one we heat it up, beat on, heat it up, beat it on, heat up, beat on it until it's in its final shape, and then we let it air cool. And that's the softest one. And then the next hardest one is the cold forged one, which we didn't give any heat at all. And the hardest one is the one we hot forged, but then we did one final step and we heat treated it. And when we heat treated it, we were able to get it quenched to get a hard enough surface to where it would cut into the other wedges instead of being cut. Sometimes we get some that are kind of close to where they kind of cut into each other, but there's always one that has cut deeper into the other one. So that's generally our most well-received lab. So that's the hot and cold forging process, and be aware of the brittle parts. Raw alloys are made using this process, hot or cold forged. Just keep that in mind for the test. Also, hammer and die forging. So hammer and die is where we have a die. We've seen a video on this in class where we have a die and a hammer comes down and slams the part into the die and creates the shape or the rough shape of the part. And generally it's done in succession and in stages. There's 3 or 4 stages of forging dies to get from the original part size to the final part size. So that's kind of the impact forging, but there's also compression forging where you just take a hot part or a cold part depending on the alloy and what process you're doing, but you take that and you put it into a giant press and it just squeezes the part into shape, and it squeezes it up against a die, or you may just be squeezing it to change the shape of the metal, but it doesn't have to be impacted. It can just be compression force, but keep in mind that compression force is a lot slower, and with the impact you can use the impact energy to your advantage to speed up the process of the forging. So at that, we're kind of getting into close to 15 minutes, so I'm going to cut this video and we'll continue on, and we're going to start getting into stress and strain in the next video. So see you guys then.